Hello friends, welcome. Friends, as you know that I have been doing some videos on deployment of Wi-Fi based technology in the 26 and the 28 gigahertz band. So yesterday I did a video which I referred to this document of TEC which lays out the specification for deploying Wi-Fi based technology over millimeter wave band, which is originally for IMT. Now this was dated 4/6/2025. And in this document, if you go down below, the power levels of the base station and the CP devices are spelled out clearly. So I'll show you where it is. And the powers are typically pretty high. And this high power can cause certain problems. So if you look at this, this is the page where it says that the base station will have a power limit of 59 dBm and the CP will have a maximum power limit of 55 dBm, 59 and 55. Now, to talk about the EMF, electromagnetic, field influence on the body, health hazard, I did a video yesterday. So if you look at this video, I'll paste the link of this video in the description, saying that if this specification were to be allowed in the 26 gigahertz band, then your Wi-Fi router will become a radiation hazard. And that is the big flaw I mentioned in the TEC draft, which needs to be corrected because this is going to be a huge health hazard. And if you go to this video, I have explained as to why it is going to be. You can't deploy the CP normally on the rooftop. You have to mount a pole of 5 meters height at least to deploy the CP in order to prevent any people coming in contact with electromagnetic wave. It's almost going to be like a base station deployed at the rooftop of a house, right? So there will be two base stations, one base station talking to multiple other base stations which are going to be located in the rooftops. Just like what we have in case of 5 gigahertz UBR, where the base station is located in a central place and there is a point to multipoint and the access points are located in the rooftop. Now in case of 26 gigahertz band, because of this high power, those CP devices which will be located in the customer premises will have to be mounted in a almost like a base station at a height of 5 meters to prevent radiation hazard. Now friends, why I am doing this video today again? Because there was a question which one of my viewers have raised, which says that if we have a beamforming and a high antenna gain, isn't the formula that I used, which is power divided by, that is EIRP divided by 4 pi r square in the denominator is wrong? Because the power doesn't spread out in all directions. So I tried to explain this using this explanation. Looks like that the viewer has not understood what I meant, right? So if you look at this response, it's saying that, so forgiving my ignorance, I was trying to say that a beam won't peak power. Sorry, I was trying to say if the beam is smaller, won't the peak power be much higher? That is, it won't be safe at won't the safe distance be higher owing to the narrow beam of the high power? Even with, let's say, Wi-Fi with less than 1 watt limit or something similar, the beam is extremely narrow. Can it cause issues? Now, friends, let me explain to you the problem statement, what is being asked, because people may get completely confused. So, let me go to my slide deck. So what we are going to understand here is the power density with beamforming. So what the viewer is trying to say, and I'm going to go straight to the slide here, is saying that, let's say if we have an antenna here, and the antenna will always have a gain. But in this case, I have assumed that the antenna does not have any gain. So it is isotropic, means the gains are all same in all directions. In a situation like this, where the gains are all same in all directions, how do you calculate power density? So you calculate the power at the antenna port, which is here, and divide this by 4 pi r square, which is the surface of the sphere. Because the area, power is what? Power density is what? Power divided by surface area. Now, if you have a smaller sphere, right, the area will be less, so power density will be high. If you have a larger sphere of radius, the area will be more, power density will be low. So as you move away from the antenna, the power density is going to reduce because the area will become large, right? This is what I mentioned. Now, suppose there is an antenna gain. The antenna gain will push the beam, the power in this solid angle. You see, this is the solid angle. Earlier, it was spread in a sphere, which I already mentioned. Now, because of this gain, biased, antenna is biasing the power within this solid angle which I marked with this black color, right? So the power is no longer here in this area. This is not here. So the power is now concentrated here, right? Now, in a situation like this, how do we calculate power density? How do we do that? Because ultimately, the power at the antenna port remains the same. But what is happening now is the power is getting concentrated in a solid angle here instead of being spread all over the sphere. Okay, so how do you calculate power density? Normally, if you look at from a calculation point of view, the power will always follow inverse square law. Whether it is a gain or not gain, it will always follow. In this direction, it will always follow inverse square law in this direction. So, if you measure power in a small area here, what will be the power density? The power density is whatever is the power which is spread out in this full area. And then that will give the power density in this area, right? So the best way to do this is what? You assume that now the power instead of P, which I assumed here, right? This is the power P here. Now I will assume that the power is no longer P, it is P multiplied by G. What is G? G is the gain of the antenna, which is nothing but focusing the beam in a narrow solid angle. Higher the gain, lower will be the solid angle, right? So it will now assume that this is the power being emanating from an isotropic antenna. Now instead of having the measuring the power density here, you assume that the power is now focused here. The full power is now P into G. G is the gain of the antenna. After you have assumed that the power is located here at the antenna port, which is P into G, then you follow the same principle what you have followed here. What is that? Same, because you now have the power into P into G located here, and now the power is now being spread, as if that it is being emanating out of an isotropic antenna. Now, if it is emanating out of the isotropic antenna, assuming the power is focused here in P into G, then it becomes very simple. P divided by 4 pi r square. Earlier there was no gain, so it was P divided by 4 pi r square. Now if this gain, P into G divided by 4 pi r square. Because power is now getting amplified because the beam is now focused here. Got it? In this solid angle. So P into G, right, is assume that is the power located here. The antenna is now having that power. Now, assume that this is an isotropic antenna. If you assume that it is an isotropic antenna, and then you assume that this is a sphere which is emanating out of this point, then it will automatically give you the calculation of power here when you do 4 pi r square. Now you get it, how the calculation is done. That is why this calculation, P into G, what I mentioned here, if you look at this, note, if you read this here, I have said that this is the worst case situation. Why do I say it's the worst case situation? Because if you are here in this place, you will notice no power because the power is now focused here. There will be nothing. Maybe there will be some side lobes here, etc. Here also there will be some side lobes. But the power is now focused here. So you have to be sitting here to get the power density, to able to get, to absorb that power density, which is P into G divided by 4 pi r square, which is nothing but P into G as if that it is an isotropic antenna and it is radiating like this. Now, you will not have nothing in these places, but the calculation upon which is going to be 4 pi r square is going to give you the power density here. You got it? It's as simple as that, right? Because power density, wherever you measure in the sphere, has to be same. If it was actual power, which is P. Then if you had measured, then what would have happened? The power density is going to be same in all the portion of the sphere. Now it is only going to be seen visible here. Now why do we do that? Why do we calculate the power density by multiplying with the gain? which kind of gives you the power which will emanate out of an isotropic antenna when you measure only in this particular portion of the sphere. Why do you do that? Because it's a worst case situation. So somebody may say that, okay, let me come out with a specification or some kind of direction that people who are standing here, they can come as close to the base station as possible. There is no problem. But if you are standing on the beam, then you cannot come near the base station by that distance. But can you have those specific rules and regulation? It will become so confusing, right? How will people know that I can't stand here, I have to stand here, I have to stand here, I can't stand here? You may be facing the beam directly. That is why this kind of calculation is done for EMF purposes. P into G, as if that it is an isotropic antenna radiating, and we calculate the power here in the solid angle. You got it now? So probably this answers this question, because if you see here, forgive me my ignorance, I was just trying to say if the beam is smaller, won't the peak power be much higher? Yes, it will be higher. That's why I have assumed it is an isotropic antenna, P into G divided by 4 pi r square. It is not just P into antenna gain. 55 dBm assumes antenna gain. Whatever the TC spec you see here, 55 dBm here, this assumes antenna gain. It has not specified how much is going to be. It could be completely isotropic also, right? Or it could be with antenna gain. If it is with antenna gain, the same principle will be followed. It does not matter, because this antenna gain has not been separated out, right? If it was suppose let's say if it was an omnidirectional, you can still will follow the same thing. 55 dBm is the total power divided by 4 pi r square. Now, if you have some antenna gain, let's say of 10 dB, then it will be 45 dB of power at the antenna port, 10 dB of antenna gain. Same situation, what I showed you here, right? Because then it will be a antenna emanating a power of 55 dBm, and assume that it is an isotropic. Why isotropic? Easy to calculate. Otherwise, you have to do some complex calculation here. You got it? So then you assume that it is an isotropic and you calculate like this. Hope that you understood. There were certain bullet points. I'm going to just run through the slide. You can pause the video and look at the slides, because that will be useful for you in case you have not understood. That is step 1. Read this. Sorry, let me just make it a rectangle, right? And then this is step 1. Step 2. Isotropic radiation is no antenna gain, radiation spread equally in all directions, power density is the distance, S is equal to P divided by 4 pi r square based on the surface area of the sphere radius, conservative baseline for safety evaluation. Step 2, diagram. Step 3, if it was directional antenna, what I do? P into G divided by 4 pi r square, what I mentioned. Peak power exposure is higher even if the total power stays same. This is a diagram. And why we are using EIRP and safety assessment? Because this is the worst case situation. EIRP is P into G, effective isotropic. The whole abbreviation of EIRP is effective isotropic radiated power, right? It is the EIRP abbreviation is effective isotropic radiated power. That is why represent the power from an equivalent isotropic radiating a radiator, allows standard power density calculation like this used in various regulators. So the real world implication: narrow beam, higher power density in one direction, safe distance increase in beam, getting tighter without knowing the beam shape or gain regulator assume worst case. Critical for high power CP like 55 dBm or for any device, right? This is the situation. So hope my viewer who asked this question here, he might have got this answer. So that's why I thought that it's a very important topic. People may not know it. That's why I did this video, to clarify doubt. So hope you have understood it. Thanks for listening till the end, and I'll come back with a new video and a new topic next time. Thank you very much, friends.